How Britain built an army of steel in 6 months, without a single factory. June 1940, Whitehall Minister of Supply Herbert Morrison stood before maps showing Britain's industrial capacity. Across the Channel, France was collapsing. The British Expeditionary Force had evacuated from Dunkirk, leaving behind nearly all its heavy equipment: tanks, artillery, vehicles, weapons, everything abandoned on French beaches. The numbers were catastrophic. Britain had fewer than 100 operational tanks on home soil. Artillery pieces numbered in the hundreds when thousands were needed. The army that had evacuated Dunkirk was intact as men, but stripped of everything required to fight modern war. And Germany was preparing invasion. Churchill's demand was impossible: rebuild the army's equipment within 6 months. Not just replace what was lost, but exceed it. Create armoured force capable of defending Britain against Wehrmacht that had just crushed France in 6 weeks. Morrison looked at the production schedules. Britain's tank factories could produce perhaps 20 tanks monthly. At that rate, equipping even one armoured division would take years. Artillery production was similarly inadequate. Small arms could be manufactured quickly, but tanks and heavy weapons required industrial capacity Britain didn't possess. The meeting was brief. Churchill was explicit: find a way. Britain has 6 months before invasion becomes possible again in spring. Use whatever methods necessary. Conventional production won't suffice. Think beyond factories. Morrison left that meeting understanding he needed to accomplish the impossible: create an army's worth of equipment without the industrial base to produce it. The realization: the solution came from unexpected source. A junior civil servant named Thomas Wright, working in procurement office, noticed something in trade statistics from previous year. Britain had been importing American scrap metal, old railway cars, bridge sections, derelict machinery at substantial volume before war disrupted shipping. Wright's memo reached Morrison's desk through bureaucratic channels. We cannot build new steel fast enough, but we possess enormous quantities of existing steel in forms no longer serving their original purposes. Every city contains thousands of tons of steel in obsolete infrastructure, unused industrial equipment, retired transport vehicles. This steel is already smelted, already shaped, already distributed throughout the country. Could it be repurposed? The idea was radical. Instead of mining ore, smelting steel, forming it into military equipment through conventional factory production, simply reconfigure existing steel objects into weapons. Take a locomotive and transform it into tank parts. Convert bridge sections into artillery shields. Reshape obsolete machinery into armoured vehicles. Morrison convened emergency meeting with metallurgists, engineers, and military procurement officers. The question was simple. Was Wright's idea possible? The metallurgists were skeptical. Steel came in different grades, formulations, tempers. Railway steel wasn't the same as armour steel. You couldn't just melt down random objects and expect consistent results suitable for military equipment. But one engineer, a man named Arthur Davies, who'd spent career working in shipyards, disagreed. Consistency isn't the issue. We're not trying to build precision instruments. We need armor plate, gun shields, tank hulls, relatively simple shapes from relatively crude steel. Railway steel is high carbon, quite strong. Bridge sections are structural grade, suitable for supports and frameworks. It won't be optimal, but it will work, and we have it now, distributed across every town in Britain, ready to be collected and reshaped. Morrison made the decision that afternoon. Britain would strip itself of obsolete steel infrastructure and convert it into military equipment through decentralized network of workshops, foundries, and improvised facilities. No single factory would produce the army's equipment. Instead, thousands of small operations would each contribute pieces, assembled into finished weapons through coordination rather than centralized production. The program was named the National Steel Reclamation Initiative. It would transform Britain into one vast distributed factory. The collection. The collection phase began within days. Government notices appeared in every newspaper, posted in every town hall, announced on BBC broadcasts. Britain needed steel, and Britain would provide it. Citizens were asked to identify obsolete steel objects in their communities, old railway equipment no longer in service, derelict bridges scheduled for replacement, unused industrial machinery, retired trams and buses, even decorative ironwork from Victorian era, gates, fences, railings deemed non-essential. The response was overwhelming. Local committees formed to coordinate collection efforts. Volunteers with cutting torches and heavy equipment descended on identified sites, systematically dismantling steel structures and preparing them for transport. The scale of the operation was unprecedented. In every town and city, teams of workers began identifying and cataloguing potential steel sources. Railway yards were surveyed for obsolete equipment. Industrial sites were assessed for unused machinery. Municipal engineers reviewed their infrastructure for structures that could be sacrificed. The psychological impact was profound. Victorian Britain had built with permanence in mind: massive iron bridges, elaborate railway stations, ornate public buildings adorned with metalwork. These structures represented 19th century confidence and prosperity. Now they were being systematically dismantled for raw material. Not everyone agreed with the program. Preservationists protested the removal of historic ironwork. Some local officials resisted surrendering infrastructure they'd maintained for decades. But the urgency was undeniable. Every ton of collected steel potentially meant another tank, another artillery piece, another weapon to defend against invasion. In Birmingham, a Victorian railway viaduct that had been replaced by modern route became a major collection target. The structure stood 60 feet high, spanning a valley with 7 massive arches. Built in 1847, it represented the pinnacle of early railway engineering, over-engineered by modern standards, constructed with far more steel than necessary by contemporary calculations. Dismantling it required 3 weeks of continuous work. Engineers surveyed the structure, identifying weak points and safe cutting sequences. Workers with acetylene torches cut through girders 3 feet thick, sections that had supported trains for nearly a century, now destined to become tank armor. As each section was cut free, cranes lowered it to trucks waiting below. The operation was dangerous. Workers operated at height with cutting equipment, dealing with steel that had been stressed by decades of use. The metal was unpredictable, sometimes cutting cleanly, other times fracturing unexpectedly as internal stresses were released. 3 workers were injured during the operation, one seriously when a section shifted during cutting and knocked him from his platform. But the work continued without pause. The viaduct yielded 400 tons of structural steel, all of it high-quality material suitable for military use. Local residents watched the dismantling with mixed feelings. The viaduct had been local landmark, visible from miles around, part of the landscape for 3 generations. Now it was being erased from the skyline, cut apart and trucked away to be melted down and reformed into weapons. In Manchester, derelict cotton mill machinery presented different challenges. The massive looms and processing equipment, made obsolete by newer technology, were complex assemblies of steel, iron, and other materials. Workers had to identify which components were valuable steel and which were worthless for military purposes. The sorting process was meticulous. Large flywheels, solid steel discs 8 feet in diameter, were clearly valuable. Drive shafts, gear assemblies, structural frameworks, all were steel that could be reclaimed. But copper wiring, brass fittings, wooden components, these had to be separated and either recycled separately or discarded. One mill alone yielded 150 tons of steel from machinery that had been sitting idle for years. The building's owner, who'd been unable to sell or profitably modernize the facility, was initially reluctant to surrender the equipment. But government compensation and patriotic duty combined to overcome his resistance. The machinery was systematically dismantled over 6 weeks, creating a mountain of sorted components ready for transport to Foundries. In London, the removal of decorative ironwork proved most controversial. Miles of Victorian railings surrounded parks, squares, and public buildings. These weren't merely functional barriers, but artistic achievements, elaborate designs incorporating floral motifs, geometric patterns, ornamental finials. They represented Victorian aesthetic values and civic pride. The government's decision to remove them sparked immediate protests. Preservation societies argued the railings were irreplaceable artistic heritage. Local residents objected to changing their neighborhood's character. Some questioned whether decorative ironwork was even suitable for military use. Wasn't it just cast iron rather than steel? But the metallurgists were clear. Much of the ironwork was indeed steel, and even cast iron could be remelted and converted to steel through proper processing. The artistic value was undeniable, but survival took precedence over aesthetics. Mary Thompson, a volunteer coordinator in Sheffield, managed collection from 30 sites in her district. Each morning, she'd receive reports of newly identified steel sources. Each afternoon, she'd dispatch crews with appropriate equipment to dismantle and transport. Her diary from those months provides detailed account of the operation's scale and complexity. August 12, 1940, survey team identified derelict railway bridge near Rotherham. Estimate 80 tons recoverable steel. Arranged cutting crew for next week. August 15th, received complaint from Town Council about removal of Market Square railings. Explained necessity. Offered to photograph railings before removal for eventual replacement. Council reluctantly agreed. August 18th, bridge cutting team reported unexpected difficulty. Steel more corroded than visible inspection suggested. Some sections unusable. Revised estimate to 60 tons. August the 22nd, 40 tons of machinery parts collected from closed foundry. Owner initially refused access. Changed mind after visit from government official. August the 28th, total collection this month 340 tons. Target was 300. Crew working 12-hour days, 6 days weekly. Fatigue becoming issue, but morale remains high. It felt like we were dismantling Britain to save Britain, she wrote in her diary. Every piece of removed railing, every section of retired bridge, every old locomotive cut apart, it represented Victorian prosperity and engineering achievement. We were literally cutting up our past to forge our future. The steel moved through improvised logistics network. Railway wagons carried bridge sections to foundries. Trucks transported machinery parts to workshops. The system was chaotic but effective, driven by urgency that eliminated usual bureaucratic delays. Within 6 weeks, 50,000 tons of reclaimed steel had been collected. Within 3 months, 200,000 tons. The quantities were staggering, representing decades of accumulated industrial infrastructure now being repurposed for immediate military necessity. The workshops converting collected steel into military equipment required distributed manufacturing approach. Britain didn't have time to build new factories, but possessed thousands of existing workshops, foundries, and facilities that could be adapted. Small workshops that normally produced agricultural equipment began manufacturing tank track links. Foundries that cast industrial components started pouring armor plate sections. Metalworking shops that made railway parts converted to producing gun mounts and turret mechanisms. The Rose Foundry in Yorkshire was a typical example. Before the war, it had produced cast iron drainage pipes and industrial fittings. In July 1940, it received 40 tons of reclaimed railway steel and instructions to produce armor plate sections for tank hulls. Owner George Rose was skeptical. "We've never worked military steel, don't have specifications or testing equipment, don't even know what thickness armor needs to be." The government engineer was blunt. "Thickness is 3 inches. Steel is what you've received. Testing will happen during assembly. Your job is to cast sections to provided templates, deliver them to collection point, and start the next batch. We need 200 sections monthly. Can you do it?" Rose looked at the templates, simple rectangular sections with bolt holes pre-marked. "Not precision work. We can do this. When do you need first batch?" "Yesterday. Actually deliver them next week and we'll call it acceptable." The foundry converted its entire operation within days. Workers who'd cast drainage pipes now cast armor sections. The techniques were similar, pouring molten steel into molds, allowing it to cool, removing and finishing, but the product was entirely different. The conversion required significant changes to the foundry's operations. The furnaces needed higher temperatures to properly melt the harder railway steel. Molds had to be reinforced to handle the different expansion characteristics. Cooling times were longer because the sections were much thicker than anything the foundry had previously produced. Rose brought in metallurgists from local university to advise on the conversion. Together, they worked out proper furnace temperatures, cooling sequences, and finishing procedures. The first batch of sections emerged after 2 weeks of experimental runs. Half were rejected, too brittle, improperly cooled, dimensions off specification, but the other half passed inspection. "We learned by doing," Rose later recalled. "No time for extensive testing or gradual refinement. We'd cast a batch, send them for inspection, adjust based on feedback, cast another batch. Within a month, our rejection rate dropped from 50% to 20%. Within 3 months, down to 10%. We became quite good at making tank armor, which was remarkable since we'd never imagined doing such work." The foundry operated continuously during peak production. 3 shifts, 8 hours each, keeping the furnaces hot and the molds in constant use. Workers who'd spent entire careers making drainage pipes now took pride in producing armor that would protect British soldiers. The change in product and purpose transformed workplace morale despite brutal working conditions. Quality was variable. Some sections were too brittle, others too soft, but the volume compensated for inconsistency. If 3 sections failed testing, the 4th usually passed. The approach was wasteful by peacetime standards, but effective under emergency conditions. Across Britain, similar transformations occurred in hundreds of facilities. Workshops that had never produced military equipment became part of distributed supply chain, each contributing specialized components that would be assembled elsewhere. The assembly challenge. Producing thousands of components in distributed workshops created unprecedented assembly challenge. How do you coordinate delivery of parts from 300 different sources to create finished tanks? The solution was modular design and flexible assembly. Engineers designed tank chassis that could accommodate variations in component dimensions. If armour sections from Yorkshire were slightly different thickness from Lancashire sections, the design allowed either to be fitted with minor modifications. Assembly occurred in improvised facilities, aircraft hangars, large warehouses, even outdoor sites under camouflage netting became tank assembly points. Components arrived from workshops across Britain, were inventoried and inspected, then assembled into finished vehicles. Lieutenant James Crawford supervised assembly operation in converted warehouse near Birmingham. Each week, trucks arrived with components, armour sections from foundries in Yorkshire, turret assemblies from workshops in Wales, track links from facilities in Scotland, engines from wherever automotive works had spare capacity. It was like world's most complicated puzzle, Crawford later recalled. Nothing fit perfectly. Every tank required modifications during assembly. We'd receive armour sections that were 2 inches too wide, so we'd cut them down. Track links that didn't quite match, so we'd file them to fit. turret rings that bound instead of rotating smoothly, requiring hours of adjustment. The assembly teams developed remarkable improvisation skills. When specified bolts weren't available, they used whatever fasteners fit. When armor sections didn't align precisely, they welded gaps or filled them with additional steel. When components arrived damaged, they repaired or modified them rather than waiting for replacements. Crawford's team consisted of 30 workers, a mix of skilled tradesmen too old for military service, reserved workers with essential skills, and women who'd learned metalworking in weeks-long training courses. They assembled tanks in the warehouse that had previously stored textiles, working under corrugated metal roof that provided minimal protection from weather. The assembly process was systematized despite the improvisation required. Each tank began on one end of the warehouse floor, marked out in chalk. The hull components were laid out and welded together first, a base plate, 4 side sections, front and rear armor. This alone took 3 days because every joint had to be welded carefully to ensure integrity. Then the turret assembly was mounted, a complex process requiring precision despite the crude components. The turret ring had to rotate smoothly, or the gun couldn't be aimed effectively. Track assemblies were fitted next, connecting dozens of individual links into continuous bands. The engine and transmission were installed from above using an overhead crane that had been part of the warehouse's original equipment. Finally, the tank was fitted with internal equipment, gun sights, communication equipment, ammunition storage, seating for crew. Much of this came from conventional military supply, but even here improvisation was necessary. When proper military radios were unavailable, civilian equipment was modified. When specified seating couldn't be obtained, simple steel frames with canvas padding substituted. Each completed tank took approximately 2 weeks to assemble, meaning Crawford's facility could produce roughly 6 tanks monthly with the current workforce. That pace frustrated him because he could see where more workers or better equipment would accelerate production. But the government had to balance resources across hundreds of similar facilities, each demanding more support than could be provided. Quality control was minimal by conventional standards. Tanks were tested by driving them around assembly facility and firing main guns at nearby quarry wall. If they moved and shot, they were declared operational and shipped to army units. The vehicles weren't elegant. Welding seams were crude. Armor sections showed visible gaps. Mechanical components rattled with imprecise tolerances. But they worked. The tanks could move. Their guns could fire. Their armor could stop expected German rounds. By October 1940, the distributed network was producing 80 tanks monthly. By December, 150 monthly. The numbers weren't matching German production, but they were transforming Britain's defensive capability from nearly nothing to substantial armored force. The artillery solution artillery presented different challenge. Tanks could be assembled from varied components, but artillery required precision. Gun barrels needed exact internal dimensions to fire accurately. Breech mechanisms required tight tolerances. Ammunition had to match gun specifications perfectly. The solution was adapting existing artillery rather than building new. Britain possessed artillery pieces from First World War, stored in depots and considered obsolete for modern warfare. These weapons were pulled from storage, refurbished, and modified with components manufactured from reclaimed steel. Gun carriages were completely rebuilt using bridge steel from demolished Victorian structures. The original wooden and iron carriages were replaced with welded steel frameworks, heavier but more durable. Shield sections were fabricated from railway steel, protecting gun crews from small arms fire and shrapnel. The modifications transformed obsolete weapons into serviceable equipment. A 1917 field gun with new carriage, shields and updated sighting equipment became adequate for 1940 defensive needs. Not optimal, not matching newer German designs, but functional and available immediately. Sarah Mitchell worked in workshop outside Leeds that specialised in artillery shield production. Her team of 8 women and 4 men, most skilled workers being either too old for military service or reserved for essential war work, produced 30 shields monthly. "We'd receive steel sections from demolished bridges," Sarah explained in post-war interview. "The steel was good quality. Structural grade meant to bear tremendous loads. We'd cut it to template specifications, drill bolt holes, shape the edges, and weld mounting brackets. Each shield weighed 200 pounds and would protect an artillery crew from everything except direct hit. The work was physically demanding and dangerous. Cutting thick steel required industrial equipment that could malfunction catastrophically. Welding heavy sections produced hazardous fumes. The workshop operated with minimal safety equipment, driven by urgency that accepted higher risks than peacetime standards would permit. Sarah had been a seamstress before the war, working in a clothing factory in Leeds city centre. She'd never imagined doing metalwork, but when the steel reclamation program began recruiting workers, she volunteered. The training was brief. 2 weeks learning basic metalworking, welding and equipment operation, then immediate assignment to production work. "The first shield I worked on took our team 5 days to complete," she recalled. "We made every mistake possible, cut the steel wrong size, drilled holes in wrong locations, botched the welding and had to grind it down and start over. Our supervisor was patient but firm. He'd show us the correct technique once, expect us to execute it properly thereafter. By the 10th shield, we'd reduced production time to 2 days. By the 20th, we could complete one in a day and a half. The workshop operated in converted barn on the outskirts of Leeds. The building had no heating beyond what the welding equipment generated, and winter mornings were brutally cold. Workers wore multiple layers under their protective equipment, and breaks were spent huddled around small stoves burning scrap wood. Despite conditions, Sarah remembered the work with pride. "Every shield we made would protect British soldiers. When you're sewing clothing, the impact of your work is abstract. When you're fabricating armor that will literally stop bullets and shell fragments, the significance is immediate and personal. Several of us had sons or husbands in the army. We knew our work might directly protect them." Despite conditions, production continued steadily. By autumn 1940, hundreds of artillery pieces had been refurbished and equipped with shields, carriages and supports manufactured from reclaimed steel. The weapons were deployed to coastal defences, formed into artillery brigades, positioned to resist invasion that everyone expected would come. The human cost. The distributed production system achieved impossible results but extracted human toll. Workshops operated long hours with minimal safety oversight. Workers handled dangerous materials, operated heavy equipment, performed tasks they'd never been trained for under conditions that prioritized speed over caution. Accidents were frequent. Thomas Wright, the civil servant whose idea had launched the entire program, maintained casualty statistics that were never publicly released. Over 6 months of peak production, 47 workers died in industrial accidents directly attributable to the steel reclamation program. Hundreds more suffered serious injuries, burns, crushed limbs, respiratory damage from foundry fumes. The first fatality occurred in July 1940, barely 2 weeks after the program began. A crane operator at a collection site in Liverpool was positioning a large section of bridge steel when the cable snapped. The 5-ton section fell, striking the operator and killing him instantly. The accident was attributed to equipment failure. The crane had been operating beyond its designed capacity, and the cable showed signs of wear that should have prompted replacement. Morrison received the report the same day. He read it carefully, authorized compensation for the worker's family, and issued a directive that all lifting equipment should be inspected before each use. But he didn't slow the collection operations. The urgency remained absolute. More accidents followed. In August, a foundry worker in Sheffield was overcome by fumes from improperly ventilated casting operation. He collapsed near an open furnace and suffered severe burns before co-workers could pull him clear. He died 3 days later in hospital. The foundry improved ventilation following the accident, but similar incidents occurred at other facilities that lacked proper safety equipment. In September, a welder at Artillery Shield Workshop in Manchester was electrocuted by faulty equipment. The welding apparatus had been operating continuously for weeks, maintained minimally, pushed beyond its designed capacity. An insulation failure caused the equipment to become energized, and when the welder touched it while standing on damp concrete floor, he was killed instantly. Each death report reached Morrison's desk with brief description of the incident and preliminary assessment of cause. He insisted on reading every report personally, refusing to delegate this responsibility. His staff noticed he aged visibly over those months, the weight of the casualties adding to the immense pressure of the overall rearmament effort. The accidents haunted Morrison. Each fatality report reached his desk with brief description. Worker killed when crane cable snapped, dropping 5-ton armor section. Foundry worker overcome by fumes from improperly ventilated casting operation. Welder electrocuted by faulty equipment operated beyond designed capacity. Morrison visited accident sites when possible, meeting with families, ensuring they received compensation and support. But he never slowed the program. The math was brutal. 47 workers had died producing equipment that might save thousands of soldiers and prevent invasion that could kill tens of thousands of civilians. "I will carry those deaths forever," Morrison wrote in private letter to his wife. Every name, every circumstance. They died building the weapons that might prevent their children from dying under German occupation. That calculus doesn't make their deaths acceptable, but it makes them necessary. I pray we never face such choices again. January 1941. Assessment. 6 months after Dunkirk, British military conducted assessment of equipment situation. The results surprised even optimistic observers. Britain now possessed 800 operational tanks, compared to fewer than 100 in June. Artillery pieces numbered 3,000, up from several hundred. Armoured cars, self-propelled guns, anti-tank weapons, all had increased dramatically. More remarkably, 80% of the equipment had been produced through the distributed network using reclaimed steel. Less than 20% came from conventional factory production. The tanks weren't sophisticated. German Panzer IV was superior in armour, firepower and reliability. But British now had numerical advantage and defensive positions. German invasion would face armoured resistance rather than nearly defenceless army. General Alan Brooke, inspecting armoured units in southern England, was candid in his assessment. These vehicles wouldn't survive long in offensive operations against prepared German positions, but for defensive warfare, particularly in Britain's favourable terrain, they're adequate. The Germans would pay terrible price trying to advance against this force. The invasion never came. Whether British defensive preparations deterred German plans, or whether Hitler's attention had already turned towards Soviet Union, remains debated. But Britain's rapid rearmament was factor in German calculations. The legacy. The National Steel Reclamation Initiative ended in spring 1941 as conventional production expanded and American Lend-Lease equipment became available. The distributed workshops returned to normal operations. The improvised assembly facilities closed. The extraordinary effort that had transformed Britain into distributed factories ceased to be necessary, but the lessons endured. Britain had demonstrated that industrial capacity wasn't limited to formal factories, that distributed production networks could achieve results centralized systems couldn't. That urgency could overcome technical limitations through sheer determination and innovative thinking. Mary Thompson, the Sheffield coordinator, kept detailed records of her district's contribution. 18,000 tons of reclaimed steel delivered to 43 different workshops, ultimately incorporated into 127 tanks, 340 artillery pieces, and countless smaller components. We proved that Britain's strength wasn't in its factories, but in its people, she wrote. Every volunteer who cut down a railing, every workshop owner who converted their facility, every foundry worker who cast armor sections, they were the factory. Britain didn't build an army in existing factories. Britain became the factory. George Rose converted his foundry back to civilian production in 1942, but kept templates from the armor sections his workers had cast. We made 2,400 sections over 18 months. Each one weighed 400 pounds, took 3 hours to cast, and would stop a German shell if welded to tank properly. I kept the templates to remind us what ordinary foundry could accomplish when extraordinary circumstances demanded it. The preserved tank. In 1985, Military Museum in Kent acquired a tank from 1940 production run. The vehicle was in remarkably good condition despite 45 years in storage. Restoration team examined it closely, documenting its construction. The tank was patchwork. Armor sections came from at least 4 different foundries, identifiable by slightly different casting marks. Track links showed 3 distinct manufacturing styles. The turret assembly used mix of standard military components and improvised parts machined in unknown workshop. Most striking was the hull's base section. Museum metallurgist identified it as railway steel from the 1880s, based on composition and microscopic examination. Somewhere in Britain, a Victorian-era railway component had been dismantled, transported to foundry, melted down and recast as tank armor, assembled into finished vehicle and deployed to defend against invasion. This tank represents triumph of improvisation over industrial limitation, the museum's director wrote in exhibition catalogue. Every component tells story of distributed manufacturing network that transformed Britain's obsolete infrastructure into military equipment when conventional production proved inadequate. It's not beautiful, but it worked. That was sufficient. Reflections. Herbert Morrison lived until 1965, serving in various government positions after the war. He rarely discussed the steel reclamation program, but in final interview before his death, he reflected on those desperate months. We did what was necessary with what we had. Britain couldn't outproduce Germany through conventional methods. We lacked the factories, the time, the resources, so we abandoned conventional methods entirely. We turned the entire nation into distributed production system using accumulated industrial infrastructure from previous century as raw material. It worked because British people made it work, not through heroic individual actions, but through sustained collective effort. Every worker who cast armor sections in converted foundry, every volunteer who dismantled obsolete infrastructure, every engineer who assembled mismatched components into functional vehicles. They built the army that defended Britain. We didn't win through superior technology or industrial capacity. We won through willingness to completely reimagine how military equipment could be produced when traditional methods failed. That's the lesson I hope endures. When conventional approaches prove inadequate, innovation and determination can create entirely new solutions from existing resources. Epilogue. The steel reclamation program was largely forgotten in post-war histories, overshadowed by later industrial achievements and military victories. Few books mentioned it. Official histories focused on conventional production and American assistance. But in workshops across Britain, older workers remembered the foundry owner who'd cast armor sections, the workshop supervisor who'd machined tank components, the assembly line worker who'd welded mismatched parts into functional vehicles. They remembered transforming obsolete railways into modern weapons. Remembered the urgency, the innovation, the sheer determination to create army from nations' accumulated industrial past. Remembered proving that Britain's strength lay not in its factories, but in its capacity to transform every workshop, every foundry, every available resource into instruments of survival. Britain built an army of steel in 6 months without a single dedicated factory by becoming the factory itself. Every reclaimed railway section, every dismantled bridge, every obsolete machine, all were transformed through distributed network of improvised facilities into the weapons that defended the nation. The tanks weren't beautiful, the artillery wasn't sophisticated, the equipment was crude by technical standards, but it existed when existence itself was the challenge. That was enough.